Okay, so here we are. So let's see, it's Wednesday. The other day, so I noticed, and I apologize for anybody who's been following the schedule. I completely screwed the schedule up and it was backwards on various days. I think it's fixed now, but we are still kind of half a day behind, but I think we'll be able to catch up just fine. The Patriots Day is possibly a makeup day, but then we're going to have, it's odd. I'm going to try to figure out. I don't think we will have any makeup days in here, even at the end of the, during reading period, because the plan is to have the final exam on the last day of class, and you can't have it during extra reading day period, so it doesn't really make sense. I will make sure that gets clarified. Speaking of exams, next Wednesday, our mid-year exam. Okay, on Monday, we will do a review for the mid-year exam. Okay, so don't stress about it. We will do a review and go kind of over everything we've talked about this semester so far and what's on the test and all that. You are allowed one back and front piece of paper with stuff on it, handwritten, none of this computer generated, bring a magnifying glass thing. I was reading a joke once, or maybe it wasn't a joke, maybe it was real life. Some professor had said, you can bring anything into the exam that you can carry, any resources you can carry into the exam. So somebody brought a graduate student in his arms into the exam, which kind of counts, I suppose. But anyway, no, you're allowed one piece of paper. You can cram a graduate student on there, lucky you. OK. A couple people have already come to me with questions about homework 4. There are some tricky things in homework 4. For instance, removing a node, how do you do it so that you end up getting all the pointers correct? It's a little bit tricky. So I'm thinking about maybe having a little kind of review session, or maybe I'll do a video or something that kind of walks through that idea, because I know it's going to be tricky. And as much as I love you guys, I don't want to answer the same question 45 times, right? But I think some of the things will be a little bit tricky. So make sure you're starting it soon if you haven't already. OK? All right, questions before we get going? All right, the other day we ended up talking about AVL trees. Who can remind me what an AVL tree invariant is? First of all, it's a binary search tree, and then what's an extra invariant? Yeah?
The depth tree, subtree is different by number of 1?
We call it the height, but yep, the height of each subtree, wherever you are in the node, wherever you are in the tree, each subtree can only differ by a height of 1. Otherwise, it's not AVL. Okay, and we learned about how to actually do this rotation, this single rotation. Let me remind you how we do this. If K1 is out of AVL-ness, whatever you want to call it, right? It's because it's 1 on this side and 1, 2, 3 on this side. Then what you have to do is rotate K1 to the left. You do so by grabbing onto this one and hoisting it up such that everything kind of falls down in order. The next one that goes, these two still stay connected, right? And K2 kind of goes up here, which means that if K2 and K1 like here, the y, which is greater than K1 but less than K2, has to go to the right of K1, which it's doing there. OK, it's a single rotation. You can do one either way, but that only happens when you have what's called a left insertion or a right insertion. In other words, you are either inserting into the right subtree of the right child, or you're inserting into the, let's say, left subtree of the left child. So far, so good? Just kind of bringing back some memories. This works only for those two cases. OK? Turns out that if you have this case where you insert, the other two cases, where you insert to the right-hand side of the left subtree, so K2's left subtree's right-hand side, or the opposite, if you were inserting into the right subtree of, or the left side of the right subtree, it doesn't actually work. Take a look what happens if you tried to rotate K2 to the right. If you hoist it up, or if you hoist up K1, well, now you've got K2 and y here. They kind of have an issue where K2 has to be to the left of y. And look, it doesn't actually change anything here. K1 now has 1 on the left and 1, 2, 3 on the right. And it's not balanced still. OK, so you have to do something a little bit different. Turns out we do what's called a double rotation, which is once you figure it out, it's getting your head wrapped around it sometimes takes a few minutes. But once you figure it out, you go, oh, I get it. It's not that bad. What you actually want to do is, because this is a right of the left subtree, you basically want to take this one and first rotate it this way so that this whole side ends up more focused, like more weighted over here, so that when you rotate this one over, it actually works. I will show you that, and we'll practice it, and you'll get the idea. Okay? You can think of it as a single rotation, but it's a little more complex. I like to think of it as these double rotations. Okay? Double or two single rotations. Okay? Here's what really happens under the covers. We basically say, remember, we're going to take this one and rotate it this way. What you have to do that is break up this little set of subtrees here, like that. I know this gets a little like confusing, but you'll see what I mean. Now you're going to rotate this way. Which one do we grab onto if we're going to rotate this one this way? K3. So I take K3 and like hoist it up here. K1 ends up to the left of K3. What's B going to do? It's going to be to the right of K1. C is still going to be to the right of K3, and A is going to be to the left of K1. Okay? So it looks like that. This one over here. Now what you can do, okay, oh, sorry, I didn't do the second rotation part. We haven't actually done the second rotation part yet. What you then do is then you rotate everything to the right. So I guess I should have had one more diagram in here. Okay? Again, we'll show you on a real trees, and we'll figure it out. Okay? Double rotation is it's the exact like equivalent for the other side, right? If you have a left child of a right that's the problem, then first you rotate this guy to the right, then you rotate this one to the left. Okay, and it actually fixes it like this. Again, I'll show you that in like more specifically. Okay? All right. So we're going to go back. I'm going to go back to the exact same picture we saw the other day, and I'm going to insert a bunch really quickly. Actually, before I do that, I'd better figure out I better write down what they are. Here, I'll do them on the board here. Big yellow chalk. What's going on under there? I don't know if I want to know. One time, when I was in college, I shouldn't even tell this story. When I was in college one time, we had a board like kind of like this, except it was one you had to, like the professor would go, and the professor comes in, and we were all sitting there, and he comes in and he swings the board up, and somebody had done a very not safe for work picture on the board, and we all were like, and he was pretty professional about it. He just erased it and whatever. But I got like secondhand embarrassment, you know, like I was way in the back, but he was like kind of embarrassed, but I was like, oh my gosh, I'd be so embarrassed. And anyway, okay, let's see, 3, 2, 1. 4, 5, 6, and then we're going to insert 16, 15, 14, 13, 12, 11, 10, 8, 9. 11, 10, 8, 9. Did I leave out 7? Oh, thank you. I even left space for it. OK. All right, so we're going to go back to here. And I'm going to make it really fast to do these first ones, because we don't need this. So 3, 2, 1. 4, 5, 5, and 6. And that was the ones we saw before, and then 7. OK, those are the ones we saw before, and we ended up with a tree that looks like this. OK, let me make it a little bigger. Whoops. OK, so that's where we ended up there. Now, if we insert 16 into this, let's see what happens. I'm going to slow it down again to some extent. OK, so we insert 16 into here. It's going to go to the right of 7. Is there going to be any problems here? See if we can figure this out. Let's see. 1 and 0, no. 0 and 0. 1, 2, 1, no. 1, 2, 3, 1, 2, no. So everybody looks OK. All right, so let's see. We'll play that. And nobody has to rotate. OK. So that was the first one. Then we're going to insert 15. And if we insert 15, let's see. Hello. Insert 15, play. There we go. All right. 15 is going to come down there. And is there a problem now? OK. Which one is the one we have a problem? How do we figure this out? Go from the one that we just inserted and start counting. This one's fine. This one, 1 and 0. It's OK. This one, 1, 2, and 0. So 7's going to be the one that's got the problem. Correct? Now, if we tried to rotate 7 immediately this way, okay, we would grab 16 and we'd hoist it up, and then it would go 16, 7, 15, and 16 would have the problem. So that's where the problem is with this single rotation happens. Does anybody want me to draw that out on the board? No? OK, you get that? That if we hoisted up 16 to try to rotate 7 this way, 16 would be come up here, 7 would go to the left of it, and then 15 would go to the right of that, and you'd still have 16 having a problem. OK? All right, so instead, we first rotate 16 this way. And so what does this one end up being? You grab 15, and it ends up just rotating 6. So 50 goes 7, 15, 16. Then if you rotate 7, it's going to end up being 15, and then, let's see, 15, and then 7, and then 16. OK, so it'll actually work. Now, the animation, it kind of almost skips a step, but I'll show you what it does here. Step forward. OK, so this says, let's see, oh, there we go, adjusting after reverse. OK, and then it says a double rotate left. That's this one. So what it's going to do is it's going to go and grab that one immediately. Want to see that again? Let's see. Oh, did I do step back already all the way? Oh, shoot. 16 was it? No, 15. 15. Insert, whoops, insert, play. There we go. OK, I'll slow it down a little bit. OK, so it's going to come up here. It's going to put 15 there. It's going to go back up, find that 7 is unbalanced, do a double rotation, and it's going to go whoop, and that's what it ends up looking like. OK? Again, it kind of jumps ahead. If you can figure out what it's doing here and get that every time, that's fine. I like to do the actual double rotations to see it work. OK? All right, let's try another one. Let's see, that was 15. Let's put 14 in. Where's 14 going to go? To there. 14, OK, so then we're going to count up. Does 7 have a problem? No. Does 15? 1 and 1, 2. OK, does 6? Yeah. 1 and 1, 2, 3. 6 has a problem. So this is the one that we're going to have to rotate. Now, which way would 6 need to rotate? 6 needs to rotate this way. But notice that we inserted 14 in the left subtree of the right child. OK? Again, this takes a little bit of time to wrap your head around. That's why I'm trying to go a little slow on this. We inserted 14 into the left subtree of the right child. So we do need a double rotation. OK? And let's keep it going, and then I'll stop it. Actually, I'll just do this. I'll step forward. OK, nope, nope. OK, double rotate left here. So what it's going to do, watch what actually happens. Boom, it does that. Now that happened too fast, right? But what we can do is we can think of it this way. I will draw this one up on the board. Don't be embarrassed for me. It's fine. OK. It's all right. That was kind of a cool little drawing there anyway. Whoops, oh no. 12. There we go. OK. All right. All right. OK. It's going to be a little tough to see with the light on here, but that's OK. So 6, I'm not going to worry, well, the 5 I need to worry about. But I'm not going to worry about anything above the 6, because it's not going to matter, right? 15, and OK, 16, and 7, and 14. Can everybody see that? OK. All right, so we said that 6 is 1, 1, 2, 3. So it's the problem. You are going to then, because you inserted 14 into the left subtree of the right child, you have to do a double rotation, meaning we can't just move 6 this way. First, we do 15 which way? To the right. So let's do that. Which one do we grab onto? Grab onto the 7. So this will become, let me write it over here. OK. This will become the 6 and the 5 are the same right now. OK. And this one becomes the 7 because we're rotating 15 this way. And then the 15 is here. And that means the 16 has to be here. And what happens to the 14? Left of 15. OK? Now we've done the single rotation that way of 7. Now we can rotate 6 the other way. Zoe? Well, because you do the opposite of what you're trying to do for the one that's wrong. So 16 needed to go this way. I'm sorry, 6. 6 needed to go this way. Right? This one's out of balance on, it's high, it's more weighted on that side, right? So we want to move it, we want to rotate it this way. 6 needs to eventually go this way. So what we do is we take its child and say, this part's the problem that's going to cause the problem, so let's make this one go this way. That's the first step. Then after that's done over here, then you're going to be able to do the 6 properly. OK, let's see if that works. OK. OK, if we're going to rotate the 6 that way, all right, which one do we grab onto? I'm going to rotate the 6 this way. We grab onto the 7. And it ends up being the 7 ends up being the root there. And then 6 ends up here. What ends up? The 5 ends up here, because it's going to be less than the 6. OK? Here we've got the 15. What happens to this 14 down here? It's going to stay here, right? And then the 16 is going to go here. Is everybody OK now? 1, 2, 1, 2, 1, 1, 1, 0. Now we're OK. All right, even though it looks kind of unbalanced, it is OK from an AVL perspective. Let's see if that's what it does up here. OK? Let's see. We've got step forward here like that. Did I get it right? Yep. OK? You see how that works? OK. So it's definitely a little bit like, whoa, what's going on? But you'll be able to figure it out when we did that. We just did the, which one did we just do? 15? We just did 14. OK, 14 we're done. So let's do a couple more. I'm not sure there's actually too many more double rotations here. Let's look at 13. You should be able to figure out which ones these are. 13's the next one that goes in. Insert, play. OK. 13 is going to go to the left of there. Is anybody out of? Let me get this down a little. Anybody screwed up now? Let's see. Let's see. 1, 2, 1. That one's OK. 1, 2, 3, 1, 2. That one's OK. 1, 2, 3, 4, 1, 2. 4 is the one. This one's the one we're going to have to rotate. Now, question for you. What do we do? What kind of rotation is it? Let's look. We put 13 down here, which according to 4 was what? The right subtree of the right child. So it's only a single rotation. Does that make sense? So we're going to have to rotate 4 which direction? 4 is going to go this way, to the left. We grab onto 7 and we hoist it up, right? And then, well, I'll show it to you, and then let's see, play. OK, hold. Oh, there we go. It's a single rotation left. And let's see if this makes sense. Aha. Right? Let's step back and see it again. Right? The 7 ends up going to the root. The 4, or the 4 ends up right below it, because you don't disconnect those. Right? And then you have to put everything that was below the 7 to the right of 4. And that's how it works. OK? One more time. Step back. And 7, we're going to rotate 4. We're going to grab onto 7, rotate it around. The 4 and the 7 stay connected. These guys have to go to the right of 4, and that's all that changes. OK? Make sense? OK. So I think that's about it for those. Let's do a few more just to practice this a little bit. OK, 12. 12 is now, oops, insert, there we go. OK, 12 goes to the left of 13. Who's going to be out of the problem? 14 is. It's a left-left, so Single rotation to the right of 14, meaning this one will just do that. So let's see. Single rotation to 14. There we go. OK. And then 12. All right. Insert 12. Going to go. Oh, I did 12 already. You guys need to stop me when I do this. 11, was it? Yeah, 11. Insert. 11 goes to the left of 12. Anybody go out of? I don't think anybody does in this case, actually. Oh, there it was. Let's go back. What happened? Oh, instead of step back. OK. I need 12. Da-da-da. OK, I'm losing it. All right, 12 and then 11. And we were on 11? Yeah, OK. 11. 11, insert, OK. So 11 goes here, and then this one's out of right, 1 and 1, 2, 3. But what is it again? What kind of rotation is it? Single, because it's the left subtree of the left child. There's another single one, so step forward. Single rotate right. I'm going to do that. And then that was 11, so now 10. For some reason, I thought I did more double rotations on here, but maybe not. OK. 10, 1, 2. Guess who's going to be a problem? 12, single rotation. There we go. And then, let's see, that was 10, 8. Maybe the reason I did 8 backwards is so do it. Insert 8. OK. There, 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 there. Is that the one that's the problem? 1, 2, 3, 4, 1, 2, 3. Oh, no, it's not even. So by the way, many times you don't have an issue, right, with these. Right? Like it's not so bad. OK, and then 9. And then 9. Oh, 9 is just going to make 10 out of, yeah. OK, what kind of rotation is this one? 10 is the one that's got the problem. Still can't get this here. 10 is the one that's got the problem. So it's a right subtree of a left child. So first we rotate which one? Nope, 10 is going to end up going to the left. You rotate 8 to the left, which is actually a really easy one. You grab on a 9 and you hoist it up, and then it goes 10, 9, 8. And then you rotate 10 to the left, to the right, and it goes 9, 8, 10. OK, like this. There you go. And that's that. OK? So you see how these things are, this isn't too bad. I know it looks like a lot of work on here, and when the trees get big, it gets a little crazy. But how about this? Somebody give me something to enter that, well, it's going to be harder than you think. Somebody suggest something that will be a double rotation for something higher up than like the bottom. Anybody want to try? What do you think? 7.5. OK. I hope we can put 7.5 in here. I'm not sure we can. OK, if we do 7.5, where's it going to go? It's going to go here, here. Oh, sorry, 7.5. This way, and then here, 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 here. OK. 1, 2, 3, 1, 2. So that's not going to be 1, 2, 3, 4. 1, 2, 1, 2, that one. So this one maybe will get through the problem. OK, let's see if it works with 7.5. Hope it does. 7.5. Insert. Good. Looks like it's going to work. Oh. Nope. I think it thought it was 75. So pay no attention to that. Is there an integer we can do, I wonder? 8's already in there. It does add another one. 8 would probably, well, I don't know. Would 8 put it to the right or the left? Not sure. We'll try it and see, just to practice this one more time. OK, 8. OK, it goes in to the right of there, but OK. So that's the one that's the problem. So which way are we going to rotate 11 eventually? To the right. So we first have to rotate this one to the left. So we grab onto 10, hoist it up, and it goes 10, 9, 8, 8. And then you will rotate this one, which will grab onto 10, and be 10, 11, all the other stuff, and then 9, 8, 8. Okay? Let's see if that does it the way I think it will. There you go. So it ends up, oh boy, what happened? It grabbed 9 instead. I think it gets confused with the numbers. Anyway, I'd be happy to come up with one that actually works, or you can look at the earlier ones here. But practice it with this if you're not getting it. You'll start to figure it out. Okay? Questions on that? This double rotation, single rotation, AVL stuff. Question on Piazza came up yesterday that said, hey, do our trees have to be AVL for this homework assignment? No. Don't worry about that. Okay? That would make this like exponentially harder. Okay? Don't worry about that. Just straight up binary search trees. If you want to go do above and beyond and try to make it AVL, by all means, go for it. But for now, you do not have to. Question? Say again? What tips you off that it's a double? If you look at the first one that you get to that has the bad balance, let's say it's 1, 2, 3, 4, 1, 2, 3, right? If it's the child of the side that's got inserted, if the child of that is the opposite of the direction you went, then it's the one. Then it's a double rotation. So remember, there's a left insert of the left child, a right insert of the right child. Those two cases are single rotation. A left insert of the right child or a right insert of the left child is a double rotation. Okay? Go look at the notes and figure out what that actually means if like processing it in your head is not easy. But in this case, like if 4 was out of, if we inserted 5 and that made 4 out of balance, 5 is to the left subtree of the right child. So that's a double rotation. Make sense? Okay, good. All right. Let's go back to here. OK, how would we actually code these up? Well, I'm not going to make you do this. This homework assignment is not about this. I will not make you do anything like code this on a test or anything crazy like that. It's relatively straightforward. You can figure out how to do rotations, right? Like you can figure out and you go, OK, this is what I have to do, this is what I have to do. It's a little bit tricky. It is definitely easiest with recursion. But recursion is not always that fast. So if you're really going to build an AVL tree, then you will do it with, probably do it with an iterative model. But here's the general ideas. Okay? First, you insert with BST, and that's what we've been doing. We can say, OK, look, it's supposed to go here. Then you check if it's, you check every node on the way back up to see if it's still AVL. If the height of a node does change, do an appropriate rotation, the single or double, and then update the heights as you go. You do have to keep the various heights as you go. And then one rotation will always suffice. OK? Somebody did code this up, and I put the little link here. If you want to go look at it, by all means, go right ahead. OK? Now, you want the dirty little secret? I feel bad telling you this now. Nobody actually uses these ones in real life. All right? Here's why. There are other rotation schemes that are more efficient. Okay? Not much, but they're more efficient. There's one that when you get into Comp 160 algorithms, you will talk about a red-black tree. Now, we could have gone over red-black trees, but you would have been ripping your hair out because you've got rotations and you have to deal with, like, what's the color of this node, red or black? And it's not worth trying to do on the first time you see rotations. So red-black trees also have rotations. They just have more invariants that go along with it. Okay? So this one is, it's kind of like the linked list of the tree world, right? It's good to learn about because it's a good learning one, but you're probably not going to really see this in real life. You're going to see something more advanced that took longer to program. Yes?
For our homework assignment, if we were to implement the AVL system, would it slow it down because like it's updating each time?
We'll talk about that. That's a good question, whether it would slow it down in something that we care about. Okay, that's the interesting part, right? What I thought you were going to ask is, if we try to do AVL, will it break the the tests? And the answer is yes, it probably will. But what you should do is do your regular one so that it works with regular BST. Put that code aside, and then have a copy that you make an AVL out of, and then figure out how to provide both. And if you really are going to do that, let me know so that I can totally look at it and go, wow, that's amazing. Okay? So great. OK. Any other questions on that one? on AVL trees. On the test, I will ask you probably to rotate something. I'll say, insert the following node. Tell me what the result is going to be. Right? Maybe tell me the steps and then tell me the result. OK? Nothing too much more than that. OK? All right. There are other different types of balanced trees. There's a thing called a 2-3 tree. There's these other ones. The AVL is the one we talk about. Red-black is the one I mentioned that most people use. I have no idea what a scapegoat tree is. A splay tree, I think a splay tree happens to be more like kind of sub-branches. And then a treep, which I don't even know what a treep is either. But we'll talk about heaps, which I believe it's kind of named after. OK? All right. Advanced reading references. OK, so that was what we were going to finish up there. Next on the agenda is actually one of my most fun, one of my favorite data structures. OK? All right. The next one is called a trie. OK? And a trie is unfortunately named, I think, because you might want to pronounce it tree, but it's a type of tree that's called a trie. And the guy who created the trie, I believe he actually named it tree, like wants it to be pronounced tree, and then everybody's like, that's silly, we've already got those. And he goes, well, I don't care anymore. And then now we just call it tries and whatever. But anyway, this is what we call a prefix tree, and we have to go into some details about that. But before we do, I want to address your problem, which is the reason I pushed you off a little bit here. We didn't really talk about the asymptotic behavior. Well, I guess we did mention the asymptotic behavior, but it's a good thing to review this. OK? Binary search trees, asymptotic behavior for find min. What's the worst case? N, because binary search trees don't have to be balanced, so it could go all the way down a linked list-like tree. Same thing for find max. If it is balanced, what's the asymptotic complexity of find min? Logarithmic. OK, and same thing for find max. OK, and this is why we like AVL trees or balanced trees in general, because we like to have trees that are balanced so that we get this logarithmic behavior. How about contains for the balanced tree? For the balanced tree, contains is you're going to basically break it in half each time, so log n still. For a unbalanced tree, it can still be n. Insert's the same. Remove, so is remove going to have a worse asymptotic complexity? Remember what we did with remove, right? We took a node and we had to go decide whether it's a leaf and then decide if it has one child or decide if it has two children. And then we make a decision if it is, and then we have to go through and delete. And if it's a double child, you have to do a bunch of replacements and all that. Is that going to change the asymptotic behavior of doing something to a balanced tree? What do you think? Explain it to your neighbor what you think, because everybody's like, no, I don't know.
What's the asymptotic behavior?
OK. When you remove, what's the first thing you have to do to remove a node? Find it. What did we say that the contains or contains is asymptotically? Log n, right, for a balanced tree. Log n. If contains is logarithmic and then you have to do more stuff to actually remove, is that going to make it slower? By definition, if you've already had to do something logarithmic, to do something else makes it slower. Does it make it slower in an asymptotic sense? Yeah, I'm seeing a couple of people saying no, and that's correct. Why no?
Because it won't increase with the more nodes that you have.
Yeah, let's look at some that they won't increase with the nodes that you have. Let's say that we were removing. Let's say that we were removing 15. OK, first things first. Logarithmic behavior, if this is pretty much balanced. 1, 2, 3, 4, 5, 6. So log base 2 of 6, which is really like 1 something, or 2 something, right? You actually have to, you find it. And then you have to do something else. In other words, you have to maybe say, OK, look, there's 2 children. I do have to go find the minimum of this one's right child, which happens to be 16. And then I have to replace the 16 here and then remove 16. But in the end, all of that taken together, all that extra stuff, is all constant stuff. You might have to go down a little bit farther to find stuff. But if you have to go down farther, where does it mean your original found node was? Up some higher, right? So there's lots of like you might in the end have to traverse all the way down to the bottom of your tree. But you never have to go back up and traverse down and go back up, and you never have to go to the other side of the tree. All of that, kind of what it all boils down to is that there's no extra logarithm or extra behavior that is based on the whole number of nodes, or even a portion of them. Okay? So remove is still asymptotically speaking. In other words, big numbers. If there were 1 million nodes in here, to do a remove is logarithmic because the rest of it's all constant behavior. Okay? So even remove is like this. So all logarithmic in this case. Okay? What if we insert into an AVL tree? Now this one's, does that change the asymptotic behavior? We insert down here. You have to walk down here. You have to walk down log n number of nodes. And then you insert. And then you have to walk back up. And you might have to do some rotations. But do you ever have to, you might have to walk, you actually definitely have to walk all the way back up to the top. So at least how many logs is that? If one down and then one more back up? 2. But do we care about constants like 2? No. So really, even if you have to do some rotations and stuff, you're still, in the big picture, not doing anything else that's going to break the asymptotic complexity of logarithmic for a tree. In other words, you have to go down all the way once, maybe. And then you have to come all the way back up once. But everything else is constant. And even those 2 logarithmic traversals is not a big deal, because we don't care about the constants. OK? It's probably more than you wanted to know. But when you get into like Comp 160 for algorithms, you'll have to go into more detail like that. But it's just the bottom line is doing an AVL like rotation is not going to affect the total asymptotic complexity of inserting into a tree. OK? So tree operations, if you're using a balanced tree, just think logarithmic. And it's actually really fast, which is good. OK? Questions on that? OK. So let's talk about these things called tries. OK, we have to do a little bit of a setup here. OK? These are called prefix trees, by the way. You'll see them called tries or prefix trees. The guy who created them named them a try. Probably not a great decision, but whatever. Oh, before I even start on this, when you guys are thinking, if you're ever thinking of getting a software engineering job, remember like the first day of class I said, this class is all about like how to get a job at Google? Remember when I said that? Well, I know people who actually have gotten interviews at, actually this one student, she's a senior right now, she got an interview at Apple because she said, oh, I used a try when I did some project in my data structures class. And they went, really? Not many people know about these tries. We want to interview you. Right? And it was like that easy, right? Because tries are one of those things that not that many people like really know that much about, but I think they're really cool. Okay? Which is part of the reason we're teaching them. The other part of the reason we're teaching them is it's probably not a bad idea to consider using this data structure for your final project in here, which is coming up in a month or so. And we should probably know about them before you try to like implement them, right? OK. You guys all have cell phones, right? You guys know Bruce Millet, right? Do you guys know the there's a website called what's it called? It's going to be, I shouldn't even say this on video. It's something like CS Students Say or something. Do you know that website? There's a website. Well, somebody put, it's basically what you guys say about like professors and other students and all that, and Halligan Hall and all that. And somebody put on there something about Bruce Millet. They're like, brilliant programmer still carries around a flip phone from like 1990. Right? And he does. He carries this like flip phone, and it's great. But anyway, most of you guys have like smartphones, right? And if you're doing a text message, right? If you're doing a text message on your smartphone, okay, does it like, you know how when you're halfway through a word, it will like auto-complete the word for you, right? And sometimes it's wrong, right? But many times it's correct, and it knows how to do it. Have you ever wondered how does it know how to auto-complete this, right? Possibly, they might do it differently at Apple, but who knows? They possibly use this thing called a try, okay, which is interesting. All right, we'll see why. Okay, so let's say we actually want to search through a dictionary. Okay, you have a dictionary. You guys even know what a dictionary is these days, like the actual paper ones, right? Everybody in college used to go off to college like carrying a dictionary with them, whatever. Anyway, so let's say we actually wanted to search through a dictionary. Okay, if we wanted to search through a dictionary in a binary search tree, we could do that. Remember how we said that it doesn't matter that we don't necessarily need to put integers or floating point values or whatever into a tree. We can put whatever we want into a tree as long as we can compare things. And you can certainly compare words, and you compare them alphabetically, right? So this might be what a binary search tree looks like for words, the following words, right? Fire, cow, red, pit, corn, sand, day, snow, pits, and fish. Okay? And notice red is farther down in the dictionary than fire, so we say that's greater than it, right? And cow is earlier in the dictionary, so it's left. But you see how this is just a binary search tree for the words, right? OK. So searching through is logarithmic. That's nice. It's relatively balanced, so that's nice. OK. We could use this, and this would not be a bad way to search through a bunch of words if we're looking through a dictionary. Not a terrible way. Logarithmic behavior is pretty good. We can do it logarithmically, right? Worst case, if it's not balanced, is still order n, not n factorial, just order n. Exclamation point being, well, it's still order n, right? But there's a lot of words that share prefixes, right? And this is a common thing about English, right? Many other languages, I don't know, does Georgian share prefixes? Like the first couple letters of words, are there lots of words that have the first couple letters? Yeah. So a lot of languages are like this. I'm not sure. Anybody speak Chinese? Probably not the same idea. Probably not like, there's no like, well, do Chinese word or characters share like strokes and things? I think a lot of them do, right? So yeah. So maybe you can do something like this, and it'd be very interesting to do this in a different language. I'm not sure how it would work, but you can do it. But there's a lot of words that share these prefixes. So if you look, cow and corn share the CO, right? And pit and pits share PIT. Those share 3 out of the 4 things. And lots of words share these prefixes. Fire and fish actually share the prefixes, right? So you have lots of these. A through Z are all the alphabet letters that we have. And words that are like 2 words will definitely share a prefix. Well, not 2 words, but if you have 27 words, at least one of them will share a prefix, right? Because you've got this idea. So we can use that, and we can use that in a very cool way to get better than logarithmic behavior. Now, we've already said that logarithmic behavior is good. What's better than logarithmic behavior? Constant behavior. OK, maybe we can get constant behavior. Who knows? OK, why limit ourselves to this binary tree? Like we've said, binary trees work great for numbers. They do. But they could work in a much different way if we, say, had a ternary tree, which would be 3 branches. Now, it gets a little tricky because you have to now keep 3 pointers together. And you have to worry about how things work out there. And you would have some more invariance if you're trying to do that. But we could do that. That would be log base 3 behavior, right? But the problem with that is, where do you stop, right? Because you've got binary tree was nice. We said, look, we've got 2. We're going to stop. We could stop at 3. And logarithmic of 3 is better than 2. But that's fine. But we've got this problem of what's called fan out. And that means that if you have many, many children, and especially if you don't set the size of those, you could have one tree with like 1 million children, and that doesn't help much at all. OK? And you have to do weird comparisons and things for that, and it's a little harder, right? But what do we know about words and the number of characters that exist? 26 characters, right? Now, you've also got uppercase characters, and you've got special symbols. And these days, you've got emojis and all those kind of things, right? But let's say you're limited to a set of characters, right? I mean, it's not going to be 2, and it's not going to be 1,000,000. It's going to be somewhere in the middle there. Okay, in our case, we're going to focus on just lowercase letters. So there are 26. We're not even going to worry about numbers right now. Okay, we're going to worry about 26 lowercase numbers. Okay, and if we do that, we have a maximum of 26 children per node, which is kind of nice. Now it's a lot, right? I mean, it's going to, if we draw this out like a regular tree, it's going to look kind of crazy. But you could have a maximum of 26 children per node because there's only 26 letters. So at least we're limiting it in that way. Okay. What we can do then, right, if we now know that we have the limit on letters, we can actually build this that's based strictly on the prefix of the words. In other words, don't take the word as a whole, break it up into its individual characters, and use those as the nodes. Okay, use the characters as the nodes. Like this. It's going to look a little funny the first time you see it, but what we can do is we can say, fine, only 1 character per node, but give them up to 26 children. Okay? Now you've got this situation where words that share prefixes only have 1 path to go through them until they stop sharing the prefix. Okay? Right? Because words tend to share lots of prefixes, you end up getting a benefit by both being able to compress the tree, although the 26 letters does give you a bit more, like it's not perfect, but it does give you a benefit in compression, and it helps out in a completely different way, which is the awesome part about it. Okay? Let's take a look at this one. Okay? Here's the same exact set of words. Okay? And now we're going to just put it in here. The root, we're going to say, doesn't have any letter. Okay? We're just going to say the root is empty. It's got a no letter, whatever you want to call it. Okay? It exists, but it's not a letter. But off of this root can be all the different letters of the alphabet, up to 26 of them. And what you can do is you can put these words in there. Like fire goes in as F-I-R-E. And the first time, in fact, I built a little thing. You'll practice this on a lab next week. But let's see if I've got it here. Where is it? www.cs.tufts.edu/comp15. What day is it? Day 12. No, lectures. Day 9, sorry. We're only up to 9 because we missed all those days. There it is. OK, fire. OK, this is a fun little program to build. You'll play around with it in lab. OK, so here's fire. Right? And it's just straight down because that's all you got so far. F-I-R-E. We have to say where a word ends, and I'll show you why that's the case in a minute. But if we add some other word, like or some of the other ones we added, cow. If we add cow to this, OK, cow does not share a prefix with fire, so we have to branch off to its own letter, C-O-W, like this. OK, and it does it like that. OK, there's your root node, and then cow like that. Okay? But if we add corn, what's going to happen to corn? Right? C-O shares, and it's going to branch right here and go R-N, right? Because it branches right there. C-O-R-N. Like that. Well, I guess I branched it the wrong way because I'm doing it alphabetically. But C-O-R-N. Okay? So that's how these ones work. Right? Let's add some of the other ones too. Let's see. Red, pit, sand. Okay, red will go in here like there. And then pit, another one we don't have a prefix for yet. Okay, and sand. Sand will, OK, I better make this a little smaller. There we go. OK, and what else did we have? Sand, day, snow, pits, and fish. Day, no, doesn't share any. Snow does. So snow is going to go where? Here, N-O-W. OK, and then fish, let's do fish next. OK, fish is going to go F-I-S-H, like that. And then pits is the last one. Now, pits is an interesting one. The whole pit fits into the word pits, right? So when we do pits, notice that we have the end of the word pit is here and the end of the word s is here. This is why we made them different colors. You could also use an asterisk or something, like is what I did on the previous page. Okay? So this is the same one we have in here, and you see how it works. Somebody give me another word to add. Yeah? Coward. Coward's a good one. C-O-W-A-R-D. Hopefully you'll see that it's going to go here and then this way and then just go whoop down like that. And it did. All right. Makes sense. Anybody want me to try another one? Yeah? No? Holding your hand up. Yeah?
Coward.
We did coward. What's? No, E-R. Oh, cower. C-O-W-E-R. OK, C-O-W-E-R will go like that, right? It just breaks it up into whatever it gets to where it stops being a prefix, then it goes the other direction and finishes the word. And if you want to figure out where a word is, you have to walk down this, and you have to figure out if the word ends. OK, we'll get to that in a second. OK, but you kind of get the basic idea here. This is what these tries look like. OK, and they are pretty neat. It comes out. OK. All right, so we have to mark where the words end so that words like pit and pits. If we didn't mark where the words ended, then we wouldn't necessarily know that pit was a word. Because you'd be coming down here and you go, well, I haven't gotten there yet. There, OK, S. Or you might say, is pi a word? Well, OK, pi. Did I tell you yesterday about pi? So do you guys know about E week, engineering week? So there's engineering week, and somebody emailed me. I have to figure out who. Probably somebody from engineering school, some student, and said, hey, Professor Greg, we're doing this pi contest. You want to participate? And here's the deal. You have to memorize a whole bunch of digits of pi. And then whatever professors memorize the least number of digits of pi, they get a pie in their face. So that means I have to go memorize all these digits. And I said, of course I said yes. So, right? So now I have to go memorize all these pies. And how many do you think I should memorize? 100? I'm going to try for like 200. Well, why not, right? I mean, it can't be that hard. I mean, who's an actor in here? Any actors? Yeah, would it be hard to memorize 200 lines? No, you can memorize. Now, numbers are a little different. There's nothing to it's not too concrete. But my idea is I'm going to play around with them a little bit. I'm going to say, you didn't tell me what base to do it in, so I'm going to recite the digits of pi in base pi, which is 1.00000, right? Yeah.
In high school, I had a friend that tried to do this as well. And the way that she did it was she based each thing into sections of phone numbers. Because typically,
oh, yeah.
to remember.
Yeah. I can't remember any phone numbers these days, though, right? I mean, now that when I was a kid, I would remember lots of phone numbers. Because I didn't have a phone in my pocket that told me these. And I didn't carry out an address book around, right? Like, there was just nothing like that. So these days, I barely know my own number, right? Some people, they'll ask me, I'm like, wait a minute, wait a minute, right? And I have to tell them. So yeah, but that's not a bad idea. I'll think about that, yeah. So anyway, if you want to come see some other professor get a pie in the face, then I'm going to beat them. I'm, got to do that. OK. So anyway, let's do as a different example. Let's say that SA is not a word, right? So if SA is not a word, we need to know that it's not a word. If we were searching for SA, we wouldn't want to stop there because we wouldn't, we want to only stop when we have markers that say it's the end of a word. Question?
How do you know when to place an word marker?
Yeah, good question. Well, when you're inserting into the try, let's take a look at this one. Let's insert dog into this. OK, you start here, and let's see. Where would you go to start here with dog? You'd go to the D, which already exists, so you don't need to put another note in there, another child there. So you go to the D, and then you check and see if the O exists, and it doesn't yet. So you go to O, and then you create an O, and then you create a G, and then what do? And then you put a marker there, and you say, we're done, right? And then when you search for it, you only stop on markers. Like you only check. So we'll talk about how to search through this. OK? But anyway, this is kind of a neat way of doing it. What are some of the benefits? Well, first benefit. OK, cost of looking up a prefix or a word is fixed. You don't ever need to go longer than the word. If I had put supercalifragilisticexpialidocious into a try, should I try it? Let's try it. I don't even think about that. Let's see. I don't know if my program will handle it. expialido. I used to fail spelling bees when I was in like sixth. I was so mad I failed a spelling bee in 6th grade, and it was like against 4th graders and stuff. And squirrel. I never knew how to spell squirrel. All right. OK, so there it is. OK, well, it's way over here. Let's see if it. Oh, there you go. Right? So yeah, it's in there, right? So if you were searching for supercalifragilisticexpialidocious, you would have to go all the way through that many letters, but never more than the number of letters in the word. Even if we put 1 billion words in the try, we never have to search more than the length of the word we happen to be searching for. That's awesome. Question? No?
Is add a lot of words functional?
Oh yeah, it is. You want to see add a lot of words? It sometimes takes a while. That should be it. There it goes. Right. I told you. That my little algorithm for printing these out was not the, like it, I did try not to make it, whoa, too bad. But anyway, yeah, there's lots of words in there now. But I don't remember what the words were. I grabbed them from the dictionary, some dictionary. OK. Anyway, all right. Yes?
Would there be a way to, so like if there was, like once you got to a letter and there were no more like break-offs from that point, you could sort of mark that, and so it just sort of assumed the rest of the word? Like,
you have to be really careful, because what if the part of the rest of the word isn't a word? You have to be careful with like making sure it's on. So we're probably not going to do it that way. The question was, do we want to mark it and say, look, the rest of the word is going to be there, but we don't know if the rest of the word, you could have variations that aren't words. And maybe I'm misunderstanding your question, but I think that's the idea.
Like for like supercalifragilisticexpialidocious, like after the first few letters, there's no more breakpoints.
Yeah.
Like,
oh,
you can mark
yeah.
it so it assumes that's
Yeah,
how it would
I see what you mean. If you assume, yeah, wait about 3 or 4 slides. You'll see what you'll see. I think we're going to get to something that you're going to go, oh, this makes sense. Good question. Let's talk about some more benefits of these tries. OK, first of all, like I said, never have to go deeper than the word length. Second of all, it is not based on the size of the vocabulary. If you put 1 billion words in this try, doesn't matter anymore, right? You don't. Your search is not based on the size. That's cool. OK, it would be kind of bad if you had 1 million or 2 million words in your dictionary, and when your phone was trying to make a prediction, it had to go through every 1 million words every time, right? It'd be super slow, right? You'd keep yelling at Siri. Right? I already yell at Siri, and I found out that Apple actually records and has somebody listen to everything you say. So when you say bad things to Siri, somebody's listening. OK, you don't need to balance it, right? There is no like balancing necessary here. It kind of self-balances. I mean, it's not really even balanced at all, but there's no need to balance because the max depth is still the word length, right? OK, here's the big question. What's the asymptotic complexity of this? What do you think? Yeah.
I would say that depends on what the longest word in like common English usage is.
That's a very good point. If you're trying to say the maximum for the words in there, but for a particular word, just the length of that word, which if we ignore constants, in other words, the length itself, what is the asymptotic complexity? Constant, right? Which is awesome. In fact, you go, whoa, wait a minute. We do get order 1 complexity. Now, more specifically, now if I asked you this on a test, I would want more specific than order 1 because we do talk about it. It's actually order of whatever word you're searching for, the length of it, right? So if you are searching for the supercalifragilisticexpialidocious in 27 letters or whatever, then you would then it would be order 27, which is still constant, right? Based on the number of things in the try. If you had 1 billion words in the try, it's still only 30 searches, which is great, right? 30 like traversals, okay? And you, so that's what I really be looking for. Constant is right for like generic case, but for a particular word, the asymptotic complexity is on the order of the length of that word, which is however many letters it is. That's cool, okay? So we've now gotten a tree structure which has constant behavior. Not bad. Are there any downsides to this? Well, of course there are. There's downsides to all these things we talk about, right? First of all, by the way, we're ignoring the complexity of letter comparisons. Isn't it true that if you're trying to figure out if, as you walk down this COW, let's say you were looking for, corn, you would compare C in the try to C in corn, and you'd compare the O, and those comparisons take a little time too. So that's another constant factor, right? So you've got like whatever the comparison time is as another constant factor. But we ignore a lot of that stuff when it comes to the big picture. Okay? They are there, though. Like you do have to do some comparisons. Okay? How would we change this to include uppercase letters? It's an idea. What do you think?
Yeah, you could just have like 52.
You could have 52. You could do 52 children. What's another solution? Yeah.
You could, in your program, just say you only take lowercase.
You can only take lowercase, right? That's a good point. Yep.
No, but like when you did it, you just convert whatever they gave you into a lowercase word.
Yeah, you have to be a little more careful, right? Because what if you had, well, it depends if you're counting like uppercase letter, lowercase letter, like in a word, and that still counts as a word or something. There's a little, but you can use tricks like that. Yeah, I agree that you could use tricks like that. Yep. What do you think?
You could have a marker like on the character that means like this is the end of a word that says if you're using this word then it needs to be capitalized.
Oh, okay. So if you have a proper noun or something, and if it's not capitalized, you might do that in the first word, first letter. Something like that maybe. And then also check in the last letter to make sure it's a word. Yeah, there's lots of little tricks. And if you added other digits and things, that's 10 more characters. Every time you add another character that's distinct, you will have to add more children. So it's not the best in that case. Yeah, question, Ben?
If you wanted all of your words to be capitalized, you could just like have that first layer of the try, make all those letters capitalized.
Yeah, just make them all capitalized. Yep, that would work. Did you have a comment or question?
Yeah, so that would assume that like James spelled with a capital J is a different word than James spelled with a lowercase.
Right, it depends on your dictionary. Right now, like on your phone, generally the phone companies or the software companies are pretty smart about it. If you started your word with an uppercase letter, it will give you suggestions of only uppercase letters. Right? So it's generally smart about that. But that gets down into what's called heuristics, which says, let's make some decisions based on the way English works in general. And it's not an algorithm you can say works every single time. Right? So, OK, good. So there are some downsizes here. Tries, while they can compress the size in the sense that you're getting the benefit of lots of similar letters, you do have lots of these, like lots of you have lots of children, right? I mean, when you ask me to do this, right? I mean, it does get a little bit crazy in terms of space, right? If we put all these words in a binary search tree, it probably wouldn't quite take up this much total space, as it turns out. Okay, so there are some issues with that. Okay, but you can compress the data pretty well. So there's some trade-offs. In the end, if you were to compare a binary search tree size to a try size, believe it or not, the try probably will lose in terms of overall size. It's probably a little bit bigger than the binary search tree equivalent. But the fact that it's now constant behavior versus logarithmic behavior makes up for the difference in most cases. Okay? If you were really worried about size, tries are probably not the perfect solution. But you can get around some of that by making these linked lists as children instead of like an array of 26. You can get around that. Makes it a little slower. Then you've got to worry about, if you're searching for Z, 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 right? It would be go down, go all the way over, linked list, to Z, go down, linked list, Z. You know what I mean? So the behavior suffers a bit if you try to compress it too much. Yeah?
So, like, theoretically, if you had a language which lacked prefixes, or not completely, but like, didn't have as many, would tries no longer be that great?
Yeah, if you had a language that didn't have a prefix-heavy syntax, then yeah, you probably wouldn't be in the best shape for these. You can also make suffix trees. I'll leave that up to you to try to figure out how you do that. But you can do suffix trees as well, which is a different idea, but similar. There, other languages maybe. I think most languages do share prefixes, though. That's what most of them do. OK, or strokes, or whatever you want to call it. OK, so now this is getting to what we had a question about earlier. we could do this. We can compress the tree such that if there aren't any further branches, and maybe this is what you were asking about, if there aren't any further branches, just say, look, put it all in one node. Right? There was a student in Ashley, she's the lab leader, or one of the lab leaders, the head TA. She actually had to implement one of these on paper at an interview, I think, for Google or something. They said, do you know about tries? She goes, I do. And they went, good, implement this compressed try for us. And she went, OK. And she did it. She actually did it fine. Now she works at Google. Well, she will next year, so that's a win. But you can notice that all you do is you say, if it doesn't branch, just put the whole word in that. Makes the data structure in the node child a little weird. Like you have to be able to account for strings and just characters. But it's possible. Can we compress this anymore? Do you notice any places where there's no branches and we haven't compressed yet? Yeah, CO and FI. You can do this a little bit more even. Right? Now you've got a pretty short try here. And you're still relying on prefixes, and it's still a try, but now you've got to deal with the fact that you could have extra parts in there. And this is, the FI is not a word, at least not yet, or at least we haven't made it a word in here, but fire is. And you have to figure that out. It just adds a little more logic to the picture. Yeah? Yeah, if you add another word that starts with F, you have to expand that FI. You have to actually expand it. So you've got to build that logic in. But if you really want to compress it, there's ways to do it. OK, there's ways to do it. OK, so let's see how we actually might do this in real life. OK, here's a try. Let's say we're searching for a word. OK, you have a root. This is just like a tree in other aspects, right? We have roots. While current is not equal to null, this is not going to be recursively searching, and it's not going to be relying on a stack or a queue. This is going to be relying on you having to walk down the tree as we did with linked lists and things. OK, so basically you say, let's see, find the child, and I'll show you what that is in a minute, of S bracket I. With strings in C++, that's how you get to a particular character. You say some string, bracket, the character number, 0 through whatever, and it will give you that. OK? If the character does not exist, in other words, if the child doesn't exist, you don't have a word, because you're searching for that character you're going through all the letters in your word, is basically what you're doing. And then you're searching for it. OK? And then when you get done with all the letters, that means that you've gone all the way down and found the end of a word, your word, but you have to decide whether or not it's in the try or not. So that's where you do this. You look, if the word marker is true, then you return that I've found a word. Otherwise, you return false. OK? So this is the logic here on how to do it. OK? You don't need to worry about memorizing that right now or taking a look at it. But it basically goes through, remember, it goes through every letter in the word and then checks the child and sees if that actually exists as a child. Yes? Let's see. Return true, else return. I guess you could probably just do it return false. Sure. No, you do.
Well, no,
because you need to go back to the next letter. Right? No, this is the next letter here. Sorry, you're right. If it's not, no, you don't. You're right, you don't. It's the only other case. Get rid of that else. OK, so here's what find child does. Now take a look at this magic. Find child, in this case, takes a character. And look what I'm returning. The character minus character A. What is that all about? Right? Characters are based on a number equals a character. Okay? You might have run into this problem where you're trying to print things out. You've heard of an ASCII table before? I actually have one here. This is an ASCII table, and it shows you what all the different letters are. Look at A. A happens to be number. You can see it right up here, 97. That's the number that corresponds to A. Guess what the number that corresponds to B is? 98, 99, 100, 101, etc. So you can actually use the fact that these are all in order, and they purposely did that. Some other encodings didn't do that. you can actually use the fact that they're in order to determine, to say which child you've got. By, let's say C was the ASCII character S. 115 minus 97 gives you what? 18, right? So it gives you 18, and if this is an array of children, which is probably the fastest way of doing it, this will return to you child 18, at position 18, right? What letter would we have to get child, what letter would be at child 17? R, right? Because R comes right before S. What child would be at 16? It's hard to go backwards in the alphabet. P, right? Q. OK, it's hard for me too. All right. 0 would be A, right? 25 would be Z. You get how that works? We've got an array of the character children, 0 through 25, because there's 26 of them. 0 corresponds to A, 1 corresponds to B, etc. OK, that's how this actually works. And what we do initially is, what do you think we set all the children equal to if they're node pointers? Initially, we just initialize them all to null. And then we can decide whether, and then when we return null, that's when we did the check to see if our child is null. That means we didn't find a word. OK? So that's how this stuff works. Okay? It's kind of neat. This stuff looks a little magical the first time you see it. You go, what am I doing? Subtracting by A. But A means 97 in ASCII. Okay? You guys know Star Wars, I hope. That's what Yoda says. Do or do not, there is no try. I don't know if he meant that, but that's what I like to think he meant. OK. Questions on this stuff? Any questions on this? Yes?
How would tries handle like hyphenated words?
Yeah, good question. How would you handle hyphenated words? OK, you could do it a couple different ways. What's one way? Add a hyphen. Yep. Or you could ignore. Right? Sometimes with words, we don't care if it's hyphenated. I mean, you just have to make those decisions when you're building a program. Yeah. What else? Other questions on this stuff? Tries, AVL trees. OK. All right. We are going to end like 2 minutes early. I'll talk to you guys Monday.